Jeez. All right. Did you get my email about homework? Since we hadn't talked about a couple of different things, I just wanted to make sure that we had actually talked about it before making you turn something in. And now it's not projecting. Are you going to project? You're just going to be a jerk today, is what you're telling me. There we go. All right. So to that end, let's talk about a couple of the concepts that were on the homework that we didn't have a chance to do examples of in class before today. So let's look at this next example in the continuous distributions where we've got a PDF given to us. It asks first for the moment generating function and then to find the values of the mean and the variance. So just like what we have for discrete distributions, we define the mean, the variance, and the moment generating functions in exactly the same way. Your mean is your expected value of x. Your variance, by definition, remember again, is the expected value of x minus mu squared, right? It's the expected value of the squares of the deviations from the mean. And your moment generating function, by definition, is the expected value of e to the tx. Those are the definitions, right, that we learned before? Yes. No. Yeah, okay, good. All right. So we did these as sums last time, right? This is the sum over everything in the sample space of x times the PMF. This is the sum over the sample space of that function times the PMF, and so on down the line. We summed it because it was a discrete distribution. Now we're talking about continuous distribution, so instead of sums, what do you think we're going to do? Integrate. Yep, exactly. So these will be defined in just the same way, except that we will be doing the integral over the sample space of each of these functions. Oops. In particular, if you've had differential equations, I don't know who in here has had it or in it currently. Some of you will be taking differential equations. This should look familiar if you've been through differential equations. This is a Laplace transform. Okay. So this also has connections to stuff that you did do in differential equations, even though it doesn't necessarily look like it from the types of problems we answer, but there are connections there. These are the definitions. Of course, your variance, you don't typically ever compute this way, right? You can still do expected value of x squared minus expected value of x quantity squared. Those same properties that we proved for expected value, that expected value breaks up over sums, that you can pull constants out of expected values, and expected value of a constant is just a constant, those all still hold for continuous distributions. Because just like with the properties we used for sums, where you can break a sum up over a sum, you can break an integral up over a sum, right? You can pull a constant out of a sum. You can pull a constant out of an integral, right? All of those properties are all the same. Okay. All right. So none of the properties that we've talked about for expected value change. Just how we're going to compute them change. Okay. All right. So this one asks us to compute the moment generating function and then compute the means. You could compute the mean, compute the mean and the variance. You could compute them directly, but we can also do it the moment generating function and take derivatives, just like what we've done before. So let's do it in order, like we typically would if we were presented this type of problem. So our moment generating function in this case is going to be the integral from 0 to infinity, because that's the interval that we're talking about. We'll do e to the tx times 1/2 x squared e to the negative x dx. I can look at these pieces here. I can add my exponents, right? And I can also factor an x out after I do that. So we can write this as integral from 0 to infinity of 1/2 x squared, pardon me, e to the, I want to write it as t minus 1 times x. All right, so now look at this integral. I notice that my integral is improper. So if I were going to properly handle it, I would replace this limit of integration with a variable and let the variable go off to infinity. I'm not going to do that. I'm going to abuse what mathematicians call abuse the notation. I'm going to leave the infinity in there. Okay. All right. So notice I've got an x squared and then e to a basically a constant times x because we're integrating with respect to x. What integration technique are we going to have to use to do that one? It's going to be parts, right? Because I can't do a simple use substitution because I don't have the right thing in front. So I'll have to do integration by parts. So just to remind, it's another reason why I'm doing this one. Just to remind, I have a u and a dv. I know being expected to remember calculus stuff is terrible, isn't it? It's so mean. What are we going to let u equal to be the u? The 1/2 x squared. I'll just pull the 1/2 out in front so I need to keep track of the constant all the time. So I'll just make it the x squared to start with, right? My dv then is the rest of it. Although the 2 will cancel the 1/2, but I'll worry about that later. Okay. We differentiate the u. We integrate the v. Differentiating the u, we get 2x dx. Oops, I lost my x on the e to the x part. Antiderivative of e to the t minus 1 times x is what? T minus 1, yep. And then e to that power, good. The t minus 1 is just a, oops. The t minus 1 is just a constant, right? So I'm just doing 1 over the constant times e to that constant. So far, so good? All right. I said I'm going to pull that 1/2 out, but when I pull the 1/2 out, I got a 2 to go with it. So the 2 will cancel it when I'm done, right? This I'll also pull out in front of everything. So we'll have a 1 over t minus, yeah, because 1 over t minus 1. And then we've got u times v. So I'll have x squared. Except I gotta be careful. I said I pulled my 1/2 out in front. My 1/2 is still here on that piece. I gotta be careful when I do that. Because it only cancels when I do the v to u. Didn't cancel on the u times v part. E to the I can pull the 1 over t minus 1 out because it's in both pieces. 1/2 x squared e to the t minus 1 times x. I still need to do that evaluated from 0 to infinity. And then remember your integration by parts formula is minus the integral of v du, right? So I'll have minus the integral from 0 to infinity. The 2 will cancel with the 1/2 this time, so those will go away. We'll just get x e to the t minus 1 x dx. So far, so good? Look familiar for integration by parts? Of the techniques of integration that you should remember, parts is probably the biggest one. I know that in Calc 2 you do trig substitution. not discounting trig substitution at all. It just doesn't come up that much after calc 2. Okay, not like I said, not discounting it at all. It just doesn't come up all that much. Partial fractions, the technique of partial fractions and being able to split things up, that process is good. Just integrating with partial fractions though doesn't necessarily come up very often either. Parts does. Actually, a buddy of mine from grad school taught for a while, but then went to go work for MasterCard. He actually contacted me one day and goes, "You're not gonna believe this. I did integration by parts in my job for MasterCard, doing data analysis types of things, but actually needed to do an integration by parts, so it was kind of funny." So of the integration techniques that you learn, use substitution and parts are probably the big ones that you need to remember. The other ones, just look them up if you actually have to do it. Okay. Just as a rule of thumb. All right. Pardon me. So before we go on to the next one, notice we're going to have to do integration by parts again. That stings, right? Okay. So before we do that, let's talk about this piece right here. Not that piece, this piece over here. Okay. I need to plug in 0. That's not hard. I plug in 0, I'm going to get 0, right? But I also need to plug in infinity, right? Well, if I plug in infinity, basically I'm taking a limit. As x goes to infinity, certainly x squared goes to infinity, right? I want this to turn out to be a value. I don't want infinity. So if this is going to be infinity, this better go to what? This piece better go to what? If it goes to something other than a certain number, it's never going to be a value. What is this going to have to go to? It better go to 0, right? To have a hope of this thing converging, remember we talked about integrals converging. To have a hope of that converging, that better go to 0, right? Okay. If just this part is going to go to 0, what better be true about your exponent? For it to go to 0, what has to be true about the exponent? It has to be negative, right? Good. What values of t are going to make that negative? One's important. It's going to be less than 1, right? It's all right. It's going to be less than 1, right? So this is actually something that has to be considered in what they call theory of moment generating functions or theory of Laplace transforms as well. In order for this thing to exist, we need to make sure that our t is less than 1. And generally speaking, for moment, and I'm just going to write this off to the side, it's always going to work for what we're going to do. But if you do more advanced things later, you may have to pay attention to it. You need to make sure that your moment generating function needs to exist, needs to be defined in a non-trivial interval around 0. Okay. It doesn't have to be very big. It can be a tiny interval, but it has to be a non-trivial interval. What I mean is that you need to have at least a little bit of stuff to the right of 0, and you need to have a little bit of stuff to the left of 0. Okay? 0 can't be an endpoint. Okay? And it also can't just be a single element set. All right? So, you just told me a second ago that as long as my t is less than 1, that will be going to 0, right? So we're okay. In particular, since t needs to be less than 1, notice that will be negative, won't it? And I do another negative here, it'll end up being positive. We'll flip it around at the end. Okay. But for right now, we're okay. All right. I just want to make sure that I mentioned this. It's important that this is not going to converge. This is not going to exist for every t. And that's okay. We only need it to converge in some interval that contains 0. Think about why. What did we use the limit generating functions to help us figure out? What values did we use the limit generating functions to help us find? Zero. For the distribution, mean and variance, right? How do we find them? First, we're taking derivatives, right? Can you differentiate an endpoint? No. That's why it has to be an interval around zero in order for it to work. Okay. It's very, very technical. You're never going to have to worry about it in this class, but it's important to mention that there really is something deeper going on behind the scenes. Okay? So, anyway, I'll stop harping on it now. Okay. But just know that that has to be true. All right. Now that this does go to zero, I'm going to do lots of hand waving here. Okay. We now have, as long as this is true, this goes to zero, that goes to infinity. Now remember, that's not enough to say it's zero, right? If you remember from Calc 1 or Calc 2 or both, we had all those indeterminate forms. 0 over 0, infinity over infinity, infinity times 0, infinity minus infinity, 0 to the 0, 1 to the infinity, infinity to the 0. There were 7. Okay? This is one of them. Right? Remember, indeterminate form literally means you can't tell by looking at it. Right? But that's what indeterminate means, is I cannot determine it. Right? Okay? Your big technique for doing indeterminate forms was make a fraction and use L'Hopital's rule. Right? That was the big technique you used, wasn't it? Make a fraction and use L'Hopital's rule. Does that sound like something I'm going to make you do if I didn't make you do limits for your improper integrals? No. So let's just talk through it real quick. If you did make a fraction, you would push this down to the denominator by making your exponent negative. And then you would differentiate the top and the bottom, right? You get a 2x on top, you get essentially the same thing on the bottom. You do it again, you get a 2 on top, and essentially the same thing on the bottom, right? So that thing on the bottom, since it's going to 0 on the top, it'll go to infinity on the bottom, so your fraction will go to 0. The bigger issue here is that if you have x to a power or e to a positive power, is going to go to infinity faster, right? The exponential functions increase faster than polynomial functions do. If you've done any CS stuff at all, or you've talked about, or discrete, or you've talked about kind of the orders, the O of n squared, those kind of things, exponential is faster than polynomial, is all we're saying there. All right. That was a lot of words for that. That's going to go to 0. I can ignore it. Okay? That was a lot of words, right? This whole thing, pardon me, this whole thing goes to 0. Okay? I know it was a lot of words, but it was important words, and then I'll never say them again. Okay? So if you've ignored what I've said the last 5 minutes, good. Okay. All right. Next part. We said we had to do integration by parts here again, right? Your u will be x, your du will be dx, your dv, again, is going to be e to the t minus 1x, and your v will be 1 over t minus 1 e to the t minus 1x. Oops, I forgot my dx up there. I did that fast because it looks exactly like what we just did, doesn't it? Just with an x instead of an x squared. It's literally the same integral otherwise. Okay, all right. Pardon me. This went to 0. I multiply my 1 over t minus 1. My 1 over t minus 1 will be still here, right? I'll make that, well, let's just do it this way. I'll just do it in pieces. 1 over t minus 1 times negative of u times v and then minus the integral of v du again. Oops. Same stuff. We're almost done. Again, we're assuming that our t is less than 1. That means this exponent is negative. So if I put in infinity, that's going to go to 0. Faster than that goes to infinity. And if I put in 0, I get 0, right? So that first integral again is going to go to 0, just like the previous one did. Do we see it? Again, we're making the assumption, just like we did in the previous part, that our t values that we're trying to plug in are ones that allow this to converge, that our t is actually less than 1 here. All right. Now, so far, I've got a minus, I'll get a minus, I forgot an extra parenthesis here. I've got a minus, so that I got a plus, and I've got 1 over t minus 1s. If I integrate again, I'm going to get another one, aren't I? So at the end here, I'll get 1 over t minus 1 cubed, e to the t minus 1x, evaluated from 0 to infinity. And I promise we are literally just about done. I'm out of integrals now. If I put in infinity, we get 0 again, right? What happens now when you put in 0? You get 1 over t minus 1 cubed, right? And we'll do 0 minus that, correct? Okay. So this will turn out to be, and I'll use the negative sign to flip my t minus 1 around. We just end up with 1 over 1 minus t quantity cubed. If you've had differential equations, if I remember correctly, when you do a Laplace transform of an x to the n, you get a s to the n plus 1 in the denominator. We started with an x squared out in front of the e to the x. We ended up with a cube in the denominator. Okay. So again, trying to relate to stuff that you would have talked about in diffie Q if you've had it. Okay. If you haven't, don't worry about it. That's okay. Okay. But it should, if you've had diffie Q, it should relate. All right. Yes. We're integrating with respect to x, so we're plugging in for x. So when we're done, we should have a function of t left. Okay. So this is our moment generating function, which looks a lot nicer than what we started with, doesn't it? Okay. All right. So now, by the way, also, your moment generating function should always be positive, because when you put it, it should be positive for the values we're interested in. And when we put it in 0, we're supposed to get 1 originally, right? Yes.
When did it? I just missed when it was. Now it's 1 minus t.
Okay, so when I put in infinity, I get 0, and then we have minus the 1 over t minus 1 cubed. I just brought it inside, since a negative 1 is the same as negative 1 cubed, and I just pulled it in. Okay. All right, so now we can use this to calculate our mean and our variance. First derivative here will be what? This is 1 minus t to the negative 3. So the first derivative is going to be negative 3, 1 minus t to the negative 4 times negative 1. Good. Second derivative is going to be
negative 12 times 1 minus t to the negative 5 times the negative 1.
So we get a 12 over 1 minus t to the 5th. The mean is 3. The variance, we have to do the second derivative evaluated at 0 minus the mean squared, right? Don't forget the minus the mean squared. I saw when I just handed back homework, I saw some people had forgot to subtract off the mean. Okay. So in this case, when we put in 0, we'll get 12, and then we'll get minus 3 squared. So we'll get 3 when we're done. I actually get 3 again. Okay. I know, I did a lot of talking. Important things. 1, we defined again what mean is, what variance is, what moment generating function is. Same exact definitions. We're just using integrals rather than sums. Second big thing, remember how to do integration by parts, because it will pop up. Okay? I know. It's a long time, right? Since you've done integration by parts. Okay. All right. And then here again, just remembering that we can still find mean and variance using our moment generating functions. That's kind of the big things out of this particular problem. Other questions on that one? By the way, if you get an integration by part problem where you have to do an improper integral, I would want you to do the same kind of argument that we did here. Don't write out the limits and use L'Hopital's rule and all that stuff. I don't expect you to do all of that. Okay. Don't tell anybody I'm letting you do that. Okay. All right. We've already talked about the first part. This is just a reminder. Remember that if we take the log of the moment generating function, we can actually figure out the mean of the variance just by plugging in the 0 into the first and the second derivative, right? If we did the log to start with. Okay. So we can do the same kind of thing here. And this one really should look like a Laplace transform if you've done Diffie-Q. This one says start with the moment generating function that's e to the negative t times 1 minus t to the negative 1. Notice again here it's talking about this restriction, making sure that we don't put in values that make it negative, okay, or make it 0 in the denominator. Use the log part and then figure out your mean and your variance. So if I have your moment generating function is e to the negative t times 1 minus t to the negative 1. What do you get when you take the natural log? So I agree with the negative t. What's going to go in between them? They're a log of a product. It's a plus, right? And then natural log of 1 minus t to the negative 1. And in fact, what else can you do with the negative 1? Bring it down. Good. This should be a minus. Right? Logs break up products into sums. And then the first part of your product was an e to the negative t, so the natural log and the e's undo each other. So that's why we're just left with the negative t. And then also remember your log property that you can bring the exponent down from. Now we're just able to do our mean and our variance by taking first and second derivatives of this function. What is the first derivative? And the first part is going to be negative 1. Yep, good. It's a minus t. I don't know why I put a plus. Second derivative. So the first derivative of the first part is going to be 0. And the other part, you'll get a negative 1, 1 minus t to the negative 2, and then times another negative 1, right? So you'll end up with a 1 over 1 minus t squared. Calculate our mean then. We'll put in 0. What do you get when you put in 0? 0, good. And calculate our variance. In this one, we can just plug the 0 into the second derivative, but again, we had to take the natural log first, right? What do you get when you put in 0 for that one? 1. Good. That one all right? Yeah, and this was more of a reminder of this. We talked about this before. Same thing applies, right? The reason why, again, is because your derivative operator, when you do with the expected value, still behaves nicely. I can do it in or out, okay? Because again, if you think about what we do, let me scroll back up. When we think about our definition here, I shouldn't say our derivative operator, our natural log operator, doesn't matter. When we do the natural log here, we would calculate whatever this function is anyway and then take the natural log. As far as the derivatives goes, though, to make sure that this actually works for what we talked about, notice that your integral here is with respect to x. When you differentiate, your moment generating function is with respect to t. So I can either differentiate with respect to t outside the integral or inside the integral. It doesn't matter. That's what I'm trying to say there. The integral with respect to x has no effect on the derivative with respect to t. Okay. All right. Anyway, doesn't matter. I was just wanted to remind. Yes. How did what turn into a negative sign? Here? Oh. Bring the exponent down in front. All right? Natural log of a to the b is b natural log of a. I'm bringing the exponent down. That's how it turned into a negative sign. By the way, that one better have turned out to be positive, right? Has to, because it's a variance. When I plug in 0, it better be positive. Otherwise, we got a problem. All right. What do we got next? Percentiles. That was one of the things I hadn't talked about. That was on the homework. All right. So here's the idea behind percentile. So when you see this little pi, which is appropriate since we're celebrating Pi Day today, don't forget pi, 130. Okay. All right. Pi, when you have the little subscript on there, is talking, at least from a probability standpoint. When you have pi with a little subscript there, it's talking about the percentile value. So this is a little bit of an idea of what we mean by percentile. Remember, if you've got some PDF, I'm going to draw it with a finite support, but it could have an infinite support. Maybe you've got a PDF that looks like this, say, for your f of x. What's the area underneath that? 1. Has to be 1, right? So when you're doing percentiles, what we're looking for is the x value so that this area up from the lowest point possible up until that point, that area is equal to the p. Okay? That's what we're looking for a percentile. Okay? We know that, think about it from a percentage standpoint. Underneath the curve is 100% of the distribution. We're looking at the value where there's just p% of the distribution up until that point. You've probably seen percentiles when you've had standardized test scores. The percentile value says that if you're at the 82nd percentile, that means 82% of the people scored worse than you. That's what that means, right? So that's what we're trying to find. Okay. Notice that this is also an accumulation idea, isn't it? We talked about the cumulative distribution function, right? So if you can find the cumulative distribution function, then you just have an equation to solve. Okay? So if f of x is the CDF, then the pth percentile is the solution to the cumulative distribution function being equal to p. It's the answer to that equation. Okay. So what I'm saying up here is that this would be equal to your cumulative distribution function evaluated at that percentile. That's what I'm saying up there. Because that's what the cumulative distribution function gives you, right? It's the accumulated probability up until that point. We want the x value that says we've accumulated p probability up until that point. So to attack this, I would personally find the cumulative distribution function first. Remember that your cumulative distribution function, by definition, is that, right? It's the probability accumulated up until a certain point. The support here starts where? -1. So I'd integrate from -1 to x of t plus 1 over 2 dt. Again, changing the variable name to make sure that we understand that it has nothing to do with the input that we're plugging in. Now, you could split it up and integrate it piece by piece, but this one is probably just as easy to integrate this as t plus 1 squared over 4. It's just a u substitution, right? I would let u equal t plus 1. Du is dt. And so then I get u squared over 4. Yes. Remember that, again, the x I'm using is my input here, right? I don't want to use the same letter here as I use in here. They aren't related to each other. So I'm just using a different letter to integrate with respect to. The letter doesn't matter. I just need to make sure it's a different letter than that one. Because again, I want to go up until x, not all the way to 1. If I go all the way to 1, I'm just going to get an answer of 1. It's a PDF. Right? I want to find, this is cumulative distribution function. I want to know how much probability has been accumulated up until this point. So I start at the bottom, and then I go to some point. I don't want to go all the way to the end, because if I go all the way to the end, I know I accumulated all of probability. I would get 1 at the end. Right? If it's a PDF, and I go from -1 to 1, I get 1. If it's going to be a PDF. Okay. So that's why I stop at some point. And if we put in our values here, we should get, I'm dragging something, x plus 1. I don't know why it's dragging now. That's weird. X plus 1 squared over 4. That's going to be annoying if I keep showing that all the time. That okay for the... Why is this thing being so weird today? Is that okay for that part? All right. So now parts A, B, and C are literally just solve an equation. Okay? And I'm just going to do it all at once. Because it doesn't matter what the subscript is, I'm going to solve the exact same equation each time, right? We agree? Okay. So if I set my x plus 1, why is that doing that? Let me cancel out of here and get back into it just to see what happens. I don't know why it looks like I'm dragging, right? There's extra little lines on there. If I had solved my x, okay, just change my pen. X plus 1 squared over, and then it looks like I'm like shaking, is I right? For the first one, it's been a week and a half. It's fine. I get pi today. I'm happy. Okay. In the first one, you would set equal to 0.64. In the second one, you would set equal to 0.25. In the third one, you would set equal to 0.81. I might as well just do it all at one and just call it P, right? Just call it whatever the number is. I don't want to solve the same equation 3 times. Let's just do it with a variable and then plug in numbers. Okay. So I would need to multiply by 4. Take the square root. Now, I'll come back to that in a second. And then subtract 1 to the other side. There's a step that I didn't say anything about. I'm going to say it now. Technically, when I take the square root of both sides, what should I put on the right-hand side? Plus or minus, right? Why did I ignore the minus? Think about what would have happened if I had a minus there at the bottom instead of a plus sign. Yeah, it'd be less than -1, wouldn't it? I'd have -1 and subtract something, correct? What's the lowest possible x value that makes any sense for this distribution? -1. So I don't know. I didn't want to subtract. I want to add something to it, right? All right. So now when we do our percentiles, your 64th percentile will be -1 plus 2 times the square root of 0.64. Square root of 0.64 is 0.8. Multiply that by 2, you get 1.6, and subtract 1, you should get 0.6. And these have to be between -1 and 1, right? If I want the 25th percentile, by the way, the reason why it uses Q1, 25th, 50th, 75th, break your distribution up into quarters, right? You have a lower 25%, 25% to 50, 50 to 75%, and an upper 25%, right? So the 25th percentile is called the first quartile, or the lower quartile, depending on which way you want to, whatever book you look at. So the lower quartile here is what Q1 is, first quartile. If it were 0.75, it would be called the third quartile. 50% is your median. So if you've heard median before, the 50th percentile is the median. So the problem asks you for the median, it just means solve this equal to 0.5. Okay? All right. First quartile then will be -1 plus 2 root 0.25. Square root of 0.25 is 0.5 times 2 is 1 minus 1 is 0. Come back to that in a second. See if that number actually makes sense for the distribution. Okay. Last one was the 81st percentile. What do you get, 0.8 when I'm done? They made it easy on me. It had numbers that I could take the square root of easily. All right. I said I wanted to come back to this one and see if it made sense. Okay. Notice that your PDF is the line x plus 1 over 2, right? So at -1, we're down at 0, and at 1, we'd be up at 1, and your graph looks like, oh, geez. Not like that. It looks very shaky. It looks like that, doesn't it? You agree? So if I just look up to 0 right here and want to know what that area is, see if it will still draw little lines with it. Come back to the other pen. If I just look at this little area here, what is the area of that? Well, that length is not 0, it's 1. It goes up to 0, and that length is 1/2. What's the area? a quarter, which is exactly what we're trying to find, right? It was the 25th percentile. We're looking for when that area is a quarter. So the 0 makes sense. That okay? Yes.
So that means it's -1 to 0.
This number here says that if I go from the lower point up to 0, that area better be 0.25. That's what that says. Yes. That okay? This is, let's just set it up. Well, actually, this one's not too hard to integrate. This one's just a matter of setting it up and making sure we understand what the problem says. This is the weekly demand for propane gas in thousands of gallons, because of course it is. Why wouldn't it be? Say you have 2,000 gallons at your warehouse. I'm guessing you don't actually store propane in a warehouse, but let's call it a warehouse. I'm guessing storing propane inside is probably, just generally speaking, a bad idea. Okay. But we'll say it's inside. Why not? We'll live dangerously. All right. If there's 2,000 gallons at the beginning of the week, what's the probability of not being able to meet the demand? What is this problem asking you to figure out?
Probably x is greater than or equal to 2.
Good. It doesn't matter if it's greater than or equal to or just greater than. I guess technically it would need to be greater than 2 because you would technically meet demand at 2. But does it matter if I have the equal sign? For continuous distributions, does it matter if I have the equal sign or not? No. Good. Does it matter for discrete distributions if I have the equal sign? Yes. Okay, good. So make sure, because you're going to have both on the next test. Great, right? Everybody's excited about it. It does not matter if I put the equal sign in there or not for a continuous distribution, because the probability for a specific value in a continuous distribution is 0 all the time. But it does matter for a discrete distribution. So you have to be careful for the discrete ones. So this is looking from 2 to infinity. I don't think I probably want to integrate that because that's an improper integral. So we're pretty used to flipping this around, right? X is less than 2. Again, I could keep the equal sign on there. Doesn't matter. Right? Doesn't matter if I put the equal sign there or not. How would we calculate this probability? Yep, of your PDF. Good, dx. Yep. This one's not so bad to integrate. It's a simple U substitution with an adjust for a negative, right? You should get 1 plus e to the negative x to the 4th, evaluated from 0 to 2. We'll get e to the negative 16th minus a 1. Which will just simplify to e to the negative 16th. Which is tiny. This is probably good for the business, right? You'd rather not run out of gas? Yes. It says they only have 2,000 gallons, right? That's all they have. And this is not being able to meet demand. They don't meet demand if the X is too big. That's why it's greater. All right. This okay? Let's do one more and then we'll get a new handout here. That sounds like fun, doesn't it? Because what we're going to do now is we're going to build different types of distributions after we get these done. All right, let's look at this one. All right, so, pardon me. An insurance agent receives a bonus if the loss ratio on his business is less than 0.5. L is the total loss, and then L is the total losses divided by the total premiums. Oof, that's a lot. Okay. So it says the bonus, well, anyway, it doesn't matter what it says because they tell you what the bonus is, right? It's 0 otherwise. So what it's asking you to figure out in this problem is an expected value of a certain function. So they tell you that if you've got a loss function, that's what this particular PDF is, the probability or the probability density function for a loss of x is given by that 3 over x to the 4th. And they ask you to didn't ask you anything. They're telling you that the total premiums is 3, and they want you to do the expected value of the bonus. So all we need to do again is when we do the expected value of the bonus, we want to do the expected value of this function relative to the PDF. We just need to know what value to integrate it over, right? So we need to figure out. So it says that the total losses divided by the total premiums needs to be less than 0.5, right? You agree? What it says it needs to be? If he's going to earn a bonus, it says the bonus is earned if the total losses divided by the total premiums is less than 0.5. So earns a bonus if x divided by t is less than 0.5. That's what the loss ratio is, right? So what's the biggest value of x? If t is 3, because that's what it says down here, right? If t is 3, what's the largest value of x that we want to consider here? What's the largest value of x for which he actually earns a bonus? 1.5, right? We need our x to be less than 1.5. So what interval, if we're going to do an expected value, what interval do we need to integrate over for this PDF? 1 to 1.5, good. So I want to do the expected value here. We'll integrate from 1 to 1.5. We know we need to put the PDF in here. That's 3 over x to the 4th. But we also need a function to go in here, right? Right? What function is going to go in there? Oh, so this is what, so we want the expected bonus, right? So it's telling us the bonus is that formula, right? X over t is going to be a part of it, I agree. Where does the x over t go in for? What is it for? L, right? The x over t is going to go in here. And t is equal to what? 3, right? So we'll have well, I didn't leave myself enough room. Of course I didn't. I'll have 0.5 minus x over 3 times 3 over 30 or 1 over 10, and then times your 3 over x to the 4th dx. So again, go through the pieces. It says the loss ratio has to be less than 0.5 before he gets a bonus, right? The loss ratio is x over t. That has to be less than 0.5. They tell you the t is 3, so x can't be bigger than 1.5 for that to be true. So that's where we got the interval from 1 to 1.5. And then this function they give you, I just had to put the x over t in for the L. And that is, once you simplify that, that's not too hard to integrate, is it? It's just x to a power. Do you need to see the integral, or can you just do it? Do you want me to do it, or can you do it? It's easier than any other integral we've done today. All right, I'll do it. That's fine. I don't mind doing it. It's math. Of course I don't mind doing it. All right. So if I distribute everything, what can I pull out? I can certainly pull out this 3/10, or I can distribute it through either way. Doesn't matter. I'll just distribute it, and then I'll worry about pulling things out. 3 over x to the 4th times a half. So you'll get 3 over, and then times a 10th as well. Sorry. A half times a 10th is a 20th. So we'll get 3 over 20 x to the 4th there. In the second one, the 3's will cancel, and so will an x. So you'll just get 1 over 10 x to the 4th in the second piece. Or x cubed, I mean, in the second piece. I assume I did my arithmetic correctly. Feels like I did. Now I need to do an antiderivative. This first one will be a negative 1 over 20x cubed. And the next one will be a 1 over 20x to the negative 2. Oops, that'll be a positive. Forgot to change my sign. I'm just anti-differentiating x to the negative 4, right? So I have to divide by negative 3 and add 1 to the exponent, so it makes it a negative 3. Here, I'm doing an x to the negative 3, so I divide by negative 2 and add 1. Oops, there should be a positive 2 on the denominator. I left it at the bottom. Sorry. All right. Notice when you plug in 1, you get 0. They're equal to each other, right? So at this point, we just have negative 1 over 20 to the 1.5 cubed plus 1 over 20 to the 1.5 squared. Anybody type that in their calculator? Because I have zero interest in doing that in my head. Okay. And notice that was in hundreds of thousands, right? So it looks like the expected bonus is going to be about what? 7,400? Move the decimal place over. Maybe it's 740. Yeah. It's moving 5 decimal places, not 6. I didn't multiply by 1,000,000. Okay. So you'd multiply by 100,000 because it says x is in hundreds of thousands here. So your expected bonus is $740. That okay? Yeah. I did plug in the 1. What do you get when you plug in 1? You get negative 1 over 20 plus 1 over 20. I get 0. Yeah. No, I plugged it in. I just got 0. By the way, that really shouldn't have been too much of a surprise. If you plug in 1, you should get 0. Because that would be exactly what I would plug in for the cumulative distribution function, and I would get 0 out. It shouldn't be too big of a surprise. Are we at least a little bit comfortable with calculating some of these things? I hope. All right, so the next section that we're talking about is gathering some new types of distributions. So much like we identified some specific types of distributions for discrete functions, or discrete distributions, I mean, we did Bernoulli, binomial, hypergeometric, geometric, negative binomial, Poisson. We did all of those from discrete distributions, right? Okay. We're going to do the same thing for continuous distributions and start to collect some of those. So if we look at this first problem, I can scroll up to it. Somewhere up here. There's lots of problems in this packet. Notice I've got some weird notation for you. This is a new notation we haven't talked about yet, right? So when we write this, what we mean on this particular one is that if I write u of a comma b, this means it's uniform on the interval from, doesn't matter if I'll use a bracket. Doesn't matter if it's a bracket or a parenthesis because it's the same as far as a probability standpoint goes. So if you think of something as uniform, what do you think of when you hear the word uniform besides maybe something you put on? What do you think of it from just, what do you think of that when you hear that word? What do you think? Was it? Consistent, right? It's the same all the time, right? So if I think about a graph of a PDF over the interval from A to B, if it should be consistent or be the same all the time, what kind of graph should I draw? A horizontal line. Good. Yep, exactly right. I should draw a horizontal line. But again, remember that what's this area under the curve have to be? 1, right? This area under here has to be 1. So if it's going to be uniform on this interval, if it's going to be a constant function all the time, I need this area to be 1. We should know the length here. What's the length of that side? Yep, it's b minus a. Good. If that's going to be b minus a, then what does your height have to be? 1 over b minus a. Good. So this is your PDF. It's a constant. So for a uniform distribution, your f of x is 1 over b minus a, where your x is between a and b. And you can contain the endpoints or not contain the endpoints. Doesn't matter, because again, the probability that you actually land on the endpoint is 0. Okay. It's going to be the same PDF either way. All right. So for part A, what's your PDF going to be? 1 over 10. Good. For x between 0 and 10. Good. That was pretty straightforward. Now, we could do our integrals. We talked about doing probabilities with integrals. However, for a uniform distribution, I think it's probably just as easy to think about the picture, right? So for any of these parts, for B or C, D and E will do something different. Actually, D makes sense. E will have to do something different. But for part B, if I think about the picture, that's my picture, isn't it? We want the probability that x is bigger than 8. We need to figure out that area. What kind of a shape is that? It's a rectangle. We want to figure out the area. Area of a rectangle is super easy, isn't it? At least I hope it's super easy at this point. Okay? What's your length or width, whichever way you want to call it? 2. Height is 1/10. So what's your probability? 1/5. Good. That's the area. That's all you have to do. You can do it with an integral if you really, really want to. Seems like overkill. If you're able to do it geometrically with areas, do it geometrically with areas. Typically, that's faster. What would you get for C? Yeah, it'd be 6/10, right? Again, thinking about your picture. Ooh, hey, I got a little crazy with my x-axis there. You have 2 to 8, and you're looking at that area. Does it matter that there's an equal sign here and not here? Nope, doesn't matter. But I can figure out that area, right? It's 6 times the 10th. Pretty straightforward, isn't it? At least I hope so. Okay. All right, so part D should be pretty easy as well. It's uniform. It's consistent. The expected value of x is the average. This is uniform over the interval from 0 to 10. What should the average be? 5. Should be halfway in between, right? Okay. In general, for a uniform, if x is uniform on the interval from a to b, then the mean will be a plus b over 2. So in this case, it'll be 5. That makes sense? Variance, let's go ahead and see if we can figure out the formula for the variance. We could do expected value of x squared minus expected value of x quantity squared. Instead, I'm going to do it by the definition, see if I can. That's the definition, right? Expected value of the square of the deviation from the mean, right? So for us, we'll do this in general. We're going to go from A to B. We'll do x minus a plus b over 2 squared, and then times the PDF, which is 1 over b minus a. Okay? Okay. Now notice that this is a constant. This is just minus a number. Basically, I have a shift. So essentially, I'm just integrating x squared, right? So this will be 1 over 3 times b minus a, x minus a plus b over 2, evaluated from cubed, evaluated from a to b. Yeah. Okay. When you plug in b, notice that you'll get a b minus a b over 2, won't we? Right? We get a b minus a b over 2. So this is going to be b minus, I need another parentheses, b minus a all over 2 cubed. When I put in a, I'll get an a, pardon me. Sorry. Notice that you'll get an a minus an a over 2. So I'll get an a minus b over 2 cubed. We see that? Okay. One more thing. I've got a negative out in front, but of course, if I cube a negative, I get a negative, right? So I've got a b minus a cubed over, that'll be over 8, and then a plus a b minus a cubed over 8. Now I have 2 of them, so it'll be over 4. Anything else nice happen? Notice both of them have a b minus a in it, so I can cancel this with those. When I add those together, I'll get over 4. So finally, we'll get b minus a squared over 12 when we're done. So for any variant, or for any uniform distribution, your variance is b minus a squared over 12. And that was pretty good timing because it's now 12:15. What's that?